So in this problem, we're told that a pair of sticks at right angles, each of mass m and length L, are balanced upon a sharp edge. They're displaced some small distance, and we're asked to find the frequency of their oscillation. So in this case, I'm actually going to use an energy calculation since energy is going to be conserved. And so in order to do that, we first need to figure out how to calculate their gravitational potential energy. We know that gravitational potential energy acts as if an object was concentrated at its center of mass, so we're just going to figure out where the center of mass is as a function of the displacement angle theta. So we know that each of the sticks is going to have center of mass halfway along its length, so that's going to be at L over 2. Since they're at right angles, we know that their half angle is pi over 4, so that tells us that this length, the distance from the connection point down to the center of mass, is going to just be L over 2 times sine of pi over 4, which is just going to be L over 2 root 2. And now we know that that is directly in between because the sticks are symmetrical about the vertical axis, and so the center of mass would have to be lying upon that axis. And so what this tells us is that if the sticks are displaced some angle theta, we're going to be able to figure out where their, or how far above their equilibrium position the center of mass is going to be. So if the equilibrium position has a distance L over 2 root 2 from our height of 0 up to the connection point of the two sticks, and at some angle theta, the center of mass is going to be up here, then all we need to do is figure out what this height here, h, is going to be. And now this is going to be a two-step process. First, we're going to figure out what this cross length here is going to be, and then we're going to use that length to figure out what h is. So we know that if we split this angle into two pieces, each with angle theta over 2, that gives us two right angles, and so each of these distances is going to be equal to L over 2 root 2 times sine theta over 2. Now since theta is very, very small, theta over 2 is also going to be very small, and we can use the small angle approximation, and so that gives us this total length is going to be 2 times L over 2 root 2 theta over 2, which is just L theta over 2 root 2. And now we know that this angle, this small angle right in here, is also going to be theta, just by doing a little bit of trig. And so that tells us that h is equal to L theta over 2 root 2 times the sine of theta, which again is approximately L theta squared over 2 root 2. So now we can use this to find the total energy. Energy is equal to mgh plus I omega squared, or 1 over 2, sorry, 1 over 2 I omega squared. We now have our function for h, so we get mg times L theta squared over 2 root 2 plus 1 over 2. I is just going to be 2/3 ml squared, and the reason for that is that this is just two uniformly distributed sticks that are both rotating about their endpoints times omega squared. We know that energy is conserved since only gravity is acting upon the stick, so dE dt is equal to 0. And then we can differentiate these terms with respect to t. We get mgl over root 2 times theta times omega plus 2/3 ml squared omega times alpha. We can cancel out the m's, the omegas, and 1 factor of L, and we end up getting theta double dot plus 3g over 2 root 2L. Theta is equal to 0. Now all we have to do is use our knowledge of harmonic motion equations, and we get that the period is equal to 2 pi times the square root of 2 root 2L over 3g, and thus the frequency is equal to 1 over 2 pi times the square root of 3g over 2 root 2L. So this is going to be our final answer for the frequency of oscillation for this system of 2 sticks rotating about a sharp edge.